Okay, thank you very much for the opportunity and of course for coming back. So I was talking about representation theory of monoids, where we had this introduction, and thanks to Alistair for the pointer, by the way. And I talked about algebras, where H reduction was a bit painful. I will come back to that later. And now I would like to talk about the monoidal categories. After Alistair's talk, it's pretty good, though, because kind of the categories Alistair liked to study, that's what I like to study from a slightly different point of view. So instead of having a category, like a diagram category, and you represent it on its obvious representation in some sense, like whatever it was in Alistair's talk, or some GLN or GLMN categories, I would like to kind of classify all representations of a category of that type. And the tool I want to use is, I hope that's not a surprise anymore, some form of cell theory and some form of H reduction. We'll see what comes up. Okay, so that's still the same setup, and now I'm going to the top part of the square. I still want to find the categorical analog. Okay, just to set up, we have plenty of examples, so don't worry that there's a lot to take into. It's not so bad, actually. I just want to make sure that what kind of categories I study. So if you study representation theory, you also need to kind of be very precise what you study, like whether you like representations of groups or monoids or maybe algebras, or maybe you like Lie algebras or Lie groups or whatever. So all of those representation theories will look very similar, and then the details are different. So I need to be quite precise what I like to study as a category. And most of these conditions are relatively harmless. So my categories should be monoidal, so I will have some nice monoidal action of a category. And there will be some field involved. Everything will be over vector spaces, so nothing too bad. There will be some additive notions involved. Maybe idempotent complete is a bit more tricky, but usually the representation theory type categories you see are idempotent complete. That just means you have direct summons as well, and not just direct sums. And I use this little symbol here, which you will see bigger anyway, so to indicate it's a direct sum. Some spaces should be finite dimensional, so it's really like a finite dimensional setup. I will give it a name in a second. And what is really crucial, and what we would discuss, so all of those is kind of, okay, yeah, we could agree on that, but I also want finitely many indecomposable objects. So first of all, I'm using additive categories, and in the additive setup, the correct notion of a simple object, and we'll come back to that in a second, of an element, should be an indecomposable object. So I don't know what a sub-object really is or something. I don't know really what a simple object is. So it should be the indecomposable object. And these are usually much more complicated to study. We'll see a lot of examples. And this is kind of a huge restriction. But we need it in order to kind of mimic. So this should be a categorical version of a finite dimensional algebra. So everything you see should be finite. In particular, the number of those guys should be finite. Why do I call it a finite dimensional algebra? Well, if you think about what would happen for such a category on some kind of Grothendieck or decategorified level, the indecomposable object will form a basis. So this is saying my basis downstairs is finite. Okay? And that's very nice. So representation theory of infinite dimensional algebras is complicated. And I don't want to touch on that. For infinite dimensional categories, infinite dimensional quotation marks, categories, it's worse. Right? So it's this huge condition. Sometimes I will have duality, sometimes I won't. Okay, there's a bicategorical version. We can ignore the bicategorical version. I'm not going to go there anyway. I'm only sticking with the monoidal categories. So here are some examples. We'll see more of them. So vector spaces. So if vector spaces do not fit into your theory, then probably you have done something wrong. So vector spaces is an example. You can check, right? All of these are clearly satisfied in vector spaces. I have one indecomposable object in vector spaces, which is the ground field. I can do something like in Alistair's talk. Alistair had super vector spaces, Z-mod 2 graded vector spaces. You can use any kind of grading by basically anything you want, and it will still satisfy those properties. My main favorite example for today, I hope we all like this one, is representations of a finite group. I might vary the field, we'll see what happens, but representations of a finite group, let's say over the complex numbers, really beautiful theory, right? So everything certainly is satisfied here. In this case, you can actually count the number of indecomposable objects because they are the simple representations. So they're given by conjugacy clauses. In general, it's a bit more complicated. But anyway. Sadly, it doesn't quite, so my story here doesn't quite work. I should talk about representations of a finite monoid, but usually the category of representations of a finite monoid is horrible, and very rarely fits into this framework. I will have categories like in Alistair's talk, categories generated by a certain object somewhere, and that depends, of course, on the choice of object, whether this list of properties is satisfied. And there are some other more fancy things which you might have heard of, like tilting modules or projective functors. So that's kind of the setup. Basically, something like representations of a group. That's what I've written up here, right? Representations of a file. Okay. So I just mark all of them for you. This one is a bit more tricky, and we'll discuss it in a second. And why is it more tricky? Because I have an arbitrary field sticking around. So as I said, the whole problem of the story, I need to be precise, so that's what I like to study. But then this property is often not satisfied, right? But this is what I need to do because in my picture here in chemistry, like I want to study some representations. It's like the matter. And in an abelian world, I would say the simples are the element. But in an additive world, the indecomposables should be the elements, but they're not really the elements. They're more like compounds. They're huge beasts in general. So simples tend to be, for example, they have a form of Schur's lemma as in Alistair's talk. Indecomposables don't need to have any form of Schur's lemma. Okay? Does it make some sense? So even for a finite group, you can have infinitely many indecomposables. You will always have finitely many simples. You can have infinitely many indecomposables. And I show you an explicit example in a second. So even this case might not fit into my framework. It will in a lot of cases, and I give you an if and only if theorem when it does, but in general it just doesn't. Right? And this is a huge obstacle, so if you want to fit your favorite category in this framework, you always, most of the time, this is the one that you would need to check. Make some sense? Awesome. Okay.
Sorry, are you calling something that satisfies all these fiat? Oh.
There you go. I'm ignoring the monoidal. So I call everything that satisfies this here. So from linear to my little box, I call it finitary. Like everything is finite, like finitary, if you want. And if it has some dualities, I would call it fiat, like finitary and adjunction, slightly misspelled if you want. So adjunction and duality is kind of a categorical. Okay, thanks Ben. So finitary are those guys. That's just to say it again, everything is finite. And if I have dualities, then I will call it fiat. So this is an example of a fiat monoidal category. Well, unless this is not satisfied. Okay. Makes some sense. For the monoid, for example, coming back to Ben's question, kind of from Monday. So when you think of the hop as a construction of the group, and the antipode is usually given as a form like this. There's, maybe I should use color. There's a -1 involved. I can't do that monoid. So monoids do not form a Hopf algebra. They still have a coproduct, so it's still monoidal and everything, but no dualities. Makes some sense. Okay, so this category already, just from this outset, is a little bit worse than the other one. So here's an explicit example. I take a finite group, a very finite one, Z mod 5. Oh, that's a very finite group. You could, nothing here special about 5. You could think about Z mod P. Okay? And I like to work over there's one bad characteristic, and I pick out exactly that one. Because otherwise, Z mod 5 has exactly 5 representations, giving 5 simple ones, and then therefore, because it's semi-simple, indecomposable ones, given by choosing a primitive fifth root of unity. The problem here is, I write it down, it's called fresh string. Nice formula. Okay, so if we have something like this, you take the fixed power, then what will happen is that you can see a lot of binomial coefficients. In this case, I probably write it now. Something like 1, 5, 10, 10, 5, 1. when in characteristic 5, all the middle bunch dies, and the only thing that remains is x to the fifth, the one here, and 1 to the fifth is a little bit boring. And this is saying there are no primitive fifth root of unity. There's only one. There's only one, namely 1. So you can't play that game anymore with the simple representations. Instead, you get those guys, which are denoted by z. So I don't have a good notion for name for indecomposable. My indecomposables are z, because it doesn't conflict with anything else. That's the only reason. And they're given as follows. Cyclic group. So I only need to tell you what the generator does. Let me say this presentation A, and I can say if it sends a generator A to the 5 matrices you see there. For example, this matrix. So if you check that, then A to the fifth is sent to this matrix 1, 0, 1, then comma 5. It's actually an identity matrix. Yeah. If you're up for the calculation, you can try the fifth one to the fifth power. It will do the same. What it will do is it will see the binomial coefficients going down the diagonal. So all of these are legal representations, but they're also all indecomposable because I just written down the Jordan blocks for you. So all of these are indecomposable representations. A bit harder to see is why these are all, but these are all indecomposable. Let me just show you, just for fun, why is number 6 missing. But I don't want to write down a 6 by 6 matrix. Let me just pretend over 0 is 2, where everything goes a bit smaller. So why is this matrix not working? You might ask. So 1, 1, 1, 1. So if you square this matrix, it needs to be 1. The 6 by 6 analog is this one here. But it isn't. So it ends up as 1s, that's fine. Ends up as 2s, that's okay, they vanish. And then you have a 1 again, so these binomials stack up on the side. Right, so this is kind of the last one. So we have five P indecomposable objects in this category. And this has just one silly simple object because I just told you that, oh yeah, it's already gone, sorry, but I just told you there's only one root of unity, it is 1. So I only have the true representation. Yeah? It has 5 times as many indecomposables as it has simple representations. In any case, this is a fiat category. There's 5 indecomposables. In all the rest, let's go back. All the rest is kind of nothing to track. Okay. Let me mention this isomorphism. How does it work? Well, we can use this trick again we had before. So if I take x minus 1 to the fifth, I would now get x to the fifth. A minus 1. A minus 1, right? To the fifth. A to the 5 is 1, A to the 5 is 1. So the isomorphism is given by sending, so this is x. So x goes input. Okay. That's no coincidence. As soon as you have 2 variables here, you're kind of dead. Let me give you an explicit example. So Z mod 5, cyclic groups, right? So here's the first not cyclic group. It's the Klein Tor group, which arises as a symmetry of upper half plane, if you want. But just algebraically, just Z mod 2 cross Z mod 2. Can't be much simpler, right? But by the same trick as before, I can use it to, well, it is actually isomorphic to group algebra, isomorphic to this polynomial ring. Now with 2 variables, and I can write down explicitly an infinite number of indecomposable objects. Note that it still has one simple object, because it's a characteristic P trick that I played. But I have infinitely many indecomposables. And here's an example. So the dots are basis vectors, and the arrows correspond to the action of x and y. And as you can see, this satisfies the relations, right? So if there's no outgoing arrow x, it means x is 0, right? So no outgoing arrow x, so x is 0. So if you start here, x 0, done. Same for y is 0, done, and so on. And all of these, well, here's the dimension. The dimension is the number of dots. works for any number of dots. So we have, it's not hard to check that these are integer possible. Here's an infinite list of integer possibles. And I'm not saying these are all, there are more. I'm not saying these are all. I just listed a few.
These all satisfy x, y equals 0 as well.
Oh, thank you very much. They also satisfy x, y equals 0. There are some others as well. The ones that don't satisfy x, y equals 0. But I only wanted to make sure here. So one simple against infinitely many integer possibles. So it is actually a tricky question. That's what I would guess. And then you have a really, really nice answer. A very general answer. And this is how it works. It's an old theorem by Hickman. And not formulated like this. So Hickman never uses the notion of a fiat category, but it's all about integer possibles. So Hickman proves this. So there are two cases. Okay, if the characteristic doesn't divide G, it's semi-simple. Simple equals integer possible. So we are happy. We always have finitely many simple integer possibles equal simples. The B case is more interesting. That's what I showed you. If the characteristic divides the order of the group, then what you need in order to have finitely many is that the p pseudo subgroups need to be cyclic. And let's double check here. The two pseudo subgroup is the group itself. It's not cyclic. There you go. You have infinitely many. And the way to prove this is actually to write down. So basically, what Hickman does is an abstract theorem that if you go down to a p pseudo and have some integer possibles upstairs, you can induce, downstairs, you can induce them upstairs. It gives you a number of integer possibles. You will get all of them. And if you already have infinitely many downstairs, you get infinitely many upstairs. And then basically it boils down to checking this case versus some case like this. Really beautiful argument. And very explicit. So you can, well, for example, here's the subgroup letters of S3, D5, A4. I didn't find S4. A5 and D6. To be read as follows. So here's S3. Here is S3 is order 6. So this is order 3 subgroup and order 2 subgroup and order 1 subgroup. This is order 10, order 5, order 2, order 1, and so on. And how do you read this? The cycled ones with the blue cycle, these are the cyclic subgroups, and the green ones are the pseudo subgroups of the corresponding. I just use characteristic 2. Right, so here they are all cyclic. So if you would study reps over S3, again it's finite. Here they are also, again, even odd issue in the dihedral group. So here they are all cyclic. So this is general. So D odd is always fiat, and characteristic 2 and even is never. So here, let me try whether I get this. 12, 6, 4, these are the Klein 4 groups. 3, 2, 1. I can just go through the divisors of 12, right? A4. So S4 already doesn't work anymore. Super explicit theorem. This is absolutely great. So all of these then fall into my cell. Let me just mention here that the Hickman theorem for monoids is completely out of reach, so monoids get completely crazy. So even the little one I showed you, the transformation monoid, has infinitely many from 5 onwards. And not just infinitely many, there's even a stronger notion. It doesn't even have finite representation. But that's also important. Monoids are really bad, and you don't have a nice theorem like Hickman. Right? Remember, now you're wondering, wait, you told us about age reduction. I was telling you about simples. These are integer possibles. So integer possibles are much, much harder. Okay. What you can always do, let me just mention this, you could take projective modules, because there will be only finitely many projective integer possibles. They all appear as direct sums of the regular representation. Or if you are like to dualize everything, you're a dual person, you could take injective modules, which is exactly the same. But it's not the same, obviously, but it has the same behavior.
But why is it not the same?
Sorry? For a group, that's right. But, okay, absolutely right. This should have been a genuine finite dimensional algebra. Sorry. That's absolutely correct. Because it's a Hopf algebra, everything is injective as projective. Alright, so here's another example, which I go through now. So I take a category generated by one object, and I'm not telling you right now what the one object is. And I just make it k-linear, additive, and complete. Now, I think Alistair called this an additive Karubi completion. Maybe I made that up, but anyway, it's very easy to add those properties. That's not very too much. So these are kind of categories like in Alistair's talk, generated by one object. Alistair had two objects because there was an orientation, but it's kind of the same. But in Alistair's talk, I think, I haven't quite checked, but I think all objects had, all categories had infinitely many indecomposable objects. So those diagram categories, Bauer, whatever, temporally, they usually have infinitely many. What you can do is you can go to some semi-simplification, but I'm showing you a different trick, what you can do to cook up a lot of fiat categories. Well, finitary categories. The dualities always depend on the object chosen. Make some sense? I take an object generated by one generator. And here's a cool trick to do this. So here's an example. So ignore the bottom part for now. I take SL2, but not the infinite group. I stick in a finite field. 2 by 2 matrices over a finite field, that's a finite group. Right? Okay. So I stick in some finite field, and that gets a bit tricky. Let me just do it on the board. I stick in some finite field. So F P to the K. Kind of generic finite field. One. And I stick it in as a coefficient of the group. And then I can choose a field, K, of characteristic P, which doesn't need to be the same. For example, I could take F4 and I could take as K F2. That's totally easy. You don't need to have anything for that. Just the character. And then the statement, which goes back to the 80s, is that you get a fiat category. For all simple, where V is any simple module of SL2. For example, vector representation. And to convince myself that this is true, you can feed the problem to the machine on the exercise sheet to find the code if you want to do it yourself. So, in this example, P equals 5. Maybe I do it this way. So P is 5. We have a 5. But the numbers are sticking here is 25. K is 2. And then the vector representation is a bit tricky. The vector representation is this one. That's not of dimension 2 over my ground field. That's of dimension 4 over my ground field, because my ground field is F5. And that's exactly what the computer tells me. So it's this one here. And these are the simple representations, or goes up to dimension 40. Okay. Do we have finitely many indecomposables? We know what to do. You can ask the computer whether the is cyclic pseudo subgroup is cyclic pseudo subgroup, and it tells you no, it's not. Good. So rep G itself is not fiat, but the subcategory spanned by all of these simple modules. I took just the vector one. Should be finite, and the computer tells me it has something like 60 indecomposable objects in total. Completely general there for SL2. Pretty cool. So constructs for you many fiat categories, and there are many statements along the same lines. I'll show you one more. So you can take any two-dimensional representations of a finite group. Duality depends on the representation, so it might end up to be only finitary, but you can really take any of them. An explicit example again. D6, remember D6 was here, so the category itself is not finitary, there's infinitely many indecomposables. But if you take this two-dimensional simple, it has only two simples, you just get a category with 3 indecomposable objects. Pretty cool statement. Any finite group, as long as it's two-dimensional, any characteristic. And this is kind of what I would like to call like kind of finite diagram categories, in the sense of what Alistair told you, because if you really take the vector representation here, you get kind of a finite version of the temporally category.
Is there some kind of control, like how big it gets by the ground field or what you get?
I don't think so. So most of these questions are really widely open, and what you see in the literature is usually a group and a characteristic in the statement that some modules give you a fiat category. It's not called a fiat category.
But do you have diagrammatics for this?
That's a really good question. So I got obsessed with those categories very recently. So for the temporality, I obviously have diagrammatics, but otherwise this is completely open.
There's some. I've been working on some.
This is really just the tip of the iceberg. There are many statements like, if you like, there are even statements about sporadic groups. The monster group in characteristic 5, here are some modules, and there should be diagrammatics for all of them, but I don't know. Right. This is a huge bunch of hopefully not too complicated fiat categories. And note that these won't be semi-simple, okay? So those guys here, for example. And those guys also won't be semi-simple. In some cases, obviously, they are if I work over the characteristic 0, for example, but most of the time. And they all fit into the theory. It's kind of cool, actually. Okay, any questions? And now, what we should do for all of these is we should come up with the cell theory. And if you're confused now, it looks exactly the same. That's the whole point. Let me say that again. So what I do is I don't run into this issue anymore that I need to fix the basis, because there is the nice basis that I would like to fix, basis in quotation marks. I take my indecomposables. So everything I'm ever going to write down is an indecomposable. All the x's, y's, and z's you see here is indecomposable. And I'm suppressing the tensor product, that might be a little bit tricky, to make it look more like the monoid case. So zx is z tensor x. And then it's exactly the same. I'm writing down, really good, but it's really exactly the same, right? So I say, oh god, what's my convention? X is left lower than y, if and only if you can find it as a direct summand, that's my final symbol, it's a direct summand of z tensor x. It's exactly the same, right? Just my symbol was different. And I get this partition of the set of indecomposables. Right? For the monoid, I get the partition of the monoid into cells. Now I partition my indecomposables, the set of indecomposables, into equivalence clauses, those left, right, and two-sided cells. Exactly, no change as before. Right? And still, they measure kind of information type of loss. In some sense, it's really the same. Just I got rid of, compared to the algebra, I got rid of this stupid choice basis. Maybe I shouldn't call it stupid, sometimes it's helpful. But here I kind of have a God-given basis if you want, whatever you call it. And this is what I call green cells in categories. Right? So what you get, green cells in categories on the set of indecomposable objects. And I don't need any duality here. Let me just say it. I use the finitary ones. You want to also get these funny categories. Let me draw the picture again. So, the picture. So we get those cells, these little blocks, sit somewhere, something. Type of letter structure. And let's say I'm interested in this guy here. What I told you what I would like to do is I would like to consider a category associated to it, and I'm using the co-set structure, the ideal structure of the cells, and I just kill everything above. This is not really above, but it's but anyway, I just kill everything above, and I get a new category, which is supported on the cell. Which supported means it is exactly the span of the indecomposable object in J. And I can do the same for one of my little H's. So here's my little H. I get Sj and Sh. You might complain now, you should complain now because I'm lying. These are not categories, these are semi-categories. Because the monoidal unit, I'll explain that now, all the things are here. Remember that for the monoid, the unit always ended in the bottom cell. The monoidal unit, for the very same reason, is smaller than everything because, well, what was it? It was y is left lower than x. If I can,
X was the
y. If I can do this way, that's also a nice symbol. But now if x is identity, I can always choose z to be y, right? My monoid unit, which is this boldface one, is always smaller than everything. Smaller or more. Left smaller, right smaller, side smaller. So it doesn't end here. It's a little bit silly. So I end up with a semi-group picture. I'm so sorry. These are semi-categories, which causes a lot of trouble if you write it down somewhere. Because literature on semi-categories is horrible. But for now, we definitely can ignore it and never just call them monoidal subcategories.
They're categories, they're just semi-monoidal. Right?
Oh, that's right. That's right. It's a typo. It's a semi-monoidal category, not a monoidal semi-category. It's a semi-monoidal category.
So, what about semi-group categories? I mean,
They're like semi-group categories, yeah. I think this is a standard one if I follow Ben and put it in front. But whatever. You can call, as long as you know what they are, you can call them whatever. Okay. That makes some sense. And of course I'm up for a classification by those guys. Let me show an explicit example. So rep S3, I already told you that rep S3 is a good one, but now I'm just going to the complex numbers. So what are my indecomposable objects? They're indexed by partitions of 3, right? What I can do, my notation for partitions of 3 is the Young diagram notation. Write it down again. This one here is the partition 1, 1, 1. This one here is the partition 2, 1. The sign representation, the trivial representation. Sorry, the standard representation and the trivial. And if you tensor together and you can decompose them, for example, if you tensor the standard itself, you will actually, because it's self-dual, you will actually see the trivial showing up. So that means the standard is smaller than the trivial, but the trivial is smaller than everything else, so the standard ends up in the little bottom block. Same for the sign representation. So this case has only one cell. And that's actually general for those guys, because you can always tensor with a dual. And being a dual means there's a map to the identity, but now you're semi-simple, so the identity splits. So the identity is always a direct summand of this picture. In other words, these guys play the role of groups in our monoid picture, where you only have one cell, everything clusters. Right? So we can write it down. There might be other categories where that happens. That's why I'm a little bit careful not to put it on the slide. But basically what we have is that rep corresponds to groups. And this is in tensor category word cuts. And this is in the word of monoids. So in the world of monoids, the groups were the only ones where you only have a trivial cell. And here, more fancy stuff will happen. But these are a huge family. So rep G is a replacement for a group in the setup, which is kind of a good thing. Anyone happy? Yeah.
This talk, you did not assume that the one is incomposable.
I didn't. I don't need that, but in this category, it of course is. It's a good point. So if I could end up in a category where the unit is not indecomposable, and then I would end up with several bottom shells. It's again more the semi-group type of picture. But in this category it is. Okay, let me vary the category. I mean the same category. Oops, this one is wrong. Ignore it. It's the same category, but in characteristic 2. Let me just write it down. So the typo, the brackets after example is wrong. I'm talking about rep. I told you it's finitary no matter what the characteristic is. What happens? Well, I have characteristic 2 coefficients. So trivial and sign representation, they're the same. Okay? So I still have 3 indecomposable objects. I have the unit, The standard survives. It's still indecomposable. It's still simple. And I have the projective cover of the unit. And I just wrote down the multiplicative table for you. Let me just one, for example, these 3. And this is easy to check. I mean, we are talking about very small. If you tender this with itself, you get it decomposes into the direct sum, the 2 standard representations. Which is the 2 representation. And exactly the opposite happens for the standard representation. So those two like each other very, very well, and they form the top cell, and the unit just ends in the bottom cell. So, very different decomposition. This is not a group-like object anymore. This is already a bit more complicated. So in some sense, semi-simple things should be group-like objects. This is not semi-simple. Yeah. And the SH in this case is just vector spaces, because there is just the monoidal unit. Upstairs it's a bit harder to say. I'm not saying it's impossible, I'm just saying I don't want to. It looks a little bit like Zmod 2, but it's not quite. Okay. And in general, you might have noticed that in this case, the top cell is given by the projective objects. I'll tell you the second one. So here, the projective cover of the trivial representation is projective. That's not a big surprise. Turns out that the other one is projective as well. They kind of like each other very much. There is this good statement that you have a projective in a category of this form, and you tensor to it anything you like, call it X. And it will decompose, sure, and it will decompose into projectives. So projectives is everything. They therefore end up at the very top. Right? The invertible ones, if you want, at the bottom, and the projectives at the top.
And they're all in one cell always, because you can tensor the regular graph?
That's right. They're really the top cell.
There's nothing else in top cell, only projectives.
Only the projectives, yes.
But
And let me mention that this is wrong here. Because if you look at the standard proofs by projective tensor projective, so this is the monoid case. This is another reason why monoids are a bit tricky as a category. So projective tensor projective in the monoid does not need to be projective, just as a warning. I won't give you an example, but I can tell you an example if you want later. And the reason is you really need the Hopf duality structure to make this work, and you don't have it. And if you don't have something, usually it goes as wrong as you want it to go. It just completely fails. Right, so here what you can have is projective tensor projective is nothing. Right, so just direct sum of, you won't even see a single projective in the decomposition. Okay. You can also do this for those categories. This is how it looks like. I'm a little bit low on time. But for all of these diagram categories, diagram type categories, the ones generated by one object, you can write down, and I have a little list of those. How does it look like? Here for the SL2 example, you get something that looks very much like higher Valente categories, but I'm not so sure. Let me just skip that. Okay. What I would like to study, so cell structure, very general, very good. We have projectives somehow, and we have invertible objects, we have a lot of crap in between. What I want to study are representations of monoidal categories, and I will be very explicit in a second. Basically, what you need to take from this slide is that what I want is a monoidal functor from my, what's my notation, probably S, to endomorphisms of a nice target category, and it should be a monoidal k-linear function. You might be worried that I only need to be k-linear, but in this setup, if it's k-linear, it's additive. Because additive is what I really should assume here. I want to talk about it.
You're denoting both the functor and then the thing is acting on by M.
I denote the functor and the thing it's acting on by M, which is a horrible notation, you're right. What I wanted to do is I wanted to denote the functor by M, and what it's acting on like a vector space, like E. That's really awkward. And what I will do is I would like those finitary fiat categories to act, and I should also tell you where to act. Right? For groups, it's kind of act on vector space. You don't need to. For groups, you can. There's a perfectly fine theory of group actions on projective spaces, for example, which is not the same as group theory on vector spaces. So I should also tell you where I act. So what is my vector space? What is my V as a lens question? And this would be a finitary category as well. So vector spaces, for example.
In most of the examples here, is the functor going to be strict?
An expert. So I secretly strictify everything, and the functor is also then strict. In general, you need to be careful, and this is the distinction, but for a talk, I don't want to talk about non-strict things. But thank you for the question. So Alistair already said that every monoidal category acts on itself. And here you go. So it's just an example of what happens. So what is it, the monoidal functor? I associate an endofunctor to each object and a natural transformation to each morphism. And the most naive one, we call it the regular representation, if you want. Because I'm allowing the same, I have finitary here and I finitary here, I can act on myself, which is kind of the reason why I want this. And that's what you get. And in a explicit example here, again S3, and let's do the characteristic 0 again. So we have 3 indecomposable objects, and they will act by endofunctors, by tensoring. So on the Gordonic level, the only thing you need to know is how the matrices look like, and I will explain the matrices now. Let me do the middle one, that's the most exciting one. So my basis I get is the basis of indecomposables. So I can just label my columns and rows by those guys. So I get a 3x3 matrix. And now my functor is acting by tensoring, let's say, with this one. So the only thing I need to do is, for example, to compute this entry and maybe this entry that. Let me compute this entry, this row. So I tensor this one, this guy, and I'm acting as this one. Turns out that this representation is a little micro-projective. This one again. I just write down 1 here, and get a 0 here. And so on. If I haven't messed up the matrix. By construction, they are all matrices with natural number entries, because I look for direct sums. Here's another one you can do. Same target, same source category, different target category. I can take a subgroup of my favorite group, E. I can take a subgroup A. Why my subgroup is H, I realize that I have no idea. Probably because I thought at one point it's too confusing with H cells. Anyway, the subgroup is K, and I can act by restriction. So I restrict my representation down and then tensor. And that's another module of this category. Here's an equivalent example. I can take S3, I can take S2, which is a perfectly legal subgroup, and I restrict my representations. That's what happens. And then the tensor product of this, for example. So this one acts as identity. This one acts, it's a sign representation, right? It swaps everything. So this guy restricts to the sum, so it acts as the sum of the two matrices. Okay? Again, everything completely in natural numbers. Right? So you only get those natural number integer value monoids. And that's about it what you can do for this category. This slide is horrible. Let me just say what I told you is kind of a solution on the Rothenberg ring. So all of these categories give a solution of a kind of a problem of how to act with integer matrices on the Rothenberg ring, but you still have a category. So you can play around in the category and you can twist the action. That's all I'm saying. You don't need to look at the details. You can twist the action.
Twisted by what?
Twisted by a course cycle. You need to twist it numerical data here. And there's a condition. So this is basically an obstruction set for still everything to be a monoidal action. So just write down the list of properties you need, and you can restrict it by a co-cycle of the subgroup. You can twist it by a co-cycle.
Sorry, I just want to make sure I understand. So if you fix the action on the growth group,
yes,
you're saying that these particular co-cycles classify all the ways that the category can act compatible with them.
That's what I'm going to say, yes. So I will have a formal statement in a second. So here the pattern is I have certain solutions on the Grothendieck level because matrix, I need to solve an equation in positive matrices.
What do you mean by solution?
You have a group that has relations. You need to write down matrices that satisfy those relations. This should satisfy the composition of groups. And each one of them, then again, can be, because it's, I mean, we still have a category. You should be able to do something to the home space. It's the twist. And it will turn out that these are all, in a certain sense. But before, I need to tell you why in what sense they are all. So that's exactly what I try to say. Right? It's something on the Grothendieck level. But I denote them by M, K for the subgroup, and what is it, phi for the twist.
So this is, we're talking about the situation of a group and a subgroup.
Yes, it's still this picture. I have group rep G acting, and I'm acting on rep K. Okay, so let me repeat what I've done here. I've specified what source and target are, right? And this is just an example. All of the examples that turn up here are, well, rep G is a fiat category in this case because background is suburbs. Rep K for the same reason is also fiat, so it perfectly fits into the setup. I skipped this. Let me just call it a categorical version. So you can ask two questions. So I would like to say what a simple representation now is. And I say it as follows. So I have two versions. One of them is on the Grothendieck level, and one of them is on the categorical level. I call the representation transitive if it's transitive in the sense of a group action. So it's non-zero, who cares? So it's non-zero. And it's generated, I will give you an explicit example in a second. And it's generated by any object. That just means the following. You think of the Grothendieck level, so the decomposables act on the category by just shifting them around, getting direct summons. The action graph you get, however it looks like, is strongly connected. That's all that's saying, right? There are no stupid pieces that you can just get away easily. And the one for the hop spaces is there are no stable ideals in the hop spaces, because if there would be stable ideals, you can just quotient out and get a smaller category. Note that the action, so the vector space is not a group, right? So in a vector space, I only have vector space structure. Here on a module category, I'm not monoidal anymore, so I only have one way of quotienting anyway, and these are exactly the ideals I need. Okay, so you don't have any strange ideals in home spaces. It's categorical. And they're called simple representation. And they play, oh yeah, so if I take this example, again the same from before, I can easily see that it's transitive by taking the direct sum of all objects, write down this matrix. Let's compare the matrix. It's just the sum of all of them. And that matrix should correspond to a collected graph by just reading this as an adjacency matrix. That's a transitivity condition. I don't have any stupid components hanging around, chilling somewhere. And in this case, the home spaces are very trivial, so there's not much to say about ideals. So all of these are examples of simple representations. You can check that for the subgroups as well. They all will be transitive, they all will be simple as well. And the co-cycles don't play any role for this property.
So Daniel, the definition of simple requires that it's transitive?
No, it follows that it's transitive. It's a good question. So So the categorical notion implies a decategorify notion. And the reason I would like to study those is, I mean, Mazurchuk and me, Mr. Walter and Vanessa were playing around with what the correct definition of a simple representation categorically is for a long time, and correct means you have your Jordan-Hölder theorem. Remember that the Jordan-Hölder theorem just tells you if you have some representation in whatever of a group or an algebra, then you have some 1 here, 2, some co-set, and all of the successive subgroups, for example, n1 and 1, are simple. That's called the Jordan-Hölder theorem. That's kind of a non-semi-simple replacement for, you can decompose it into simples. In general, you can't decompose it. You get the Jordan-Hölder theorem. And here you have the same. And that's why you would like to classify them in the usual question of that you would like to write down kind of a periodic table of those simples. It's absolutely not clear whether you can do it. It's absolutely not clear whether you should expect a finite answer. But that's kind of what I would like to do. And to give you an example, of course, I'm not sure who actually did that. I contributed this to Ognianu. I learned it from a paper of Victor's where they, I think, just repeat this classification, but you can correct me if that's wrong. So that's how a classification should look like. It's complete. Each and every single one of those form subgroup co-cycle. Remember, K was a subgroup of a fixed graph G, subgroup of G, and there is some condition. So there's the same if and only if the subgroups are the same if and only if the subgroups are conjugate, and the co-cycles are conjugate in the sense of they have the same homology class. They're co-cycles, so they have the same homology class. That's pretty cool. It's a pretty cool statement. So we get a very finite list. You list subgroups. Yeah, here's an example. You list subgroups, which is a very finite problem. S3. Let's focus on S3. What are the subgroups of S3? Well, it's S3 up to conjugacy. Z mod 3, Z mod 2 in the trivial group. I count them up to conjugacy. That's what I need to do as well. In this case, there's just one up to conjugacy, but it might not be true in general. And I ask a computer to calculate the homology. Okay. And it's trivial in all those cases. There you go. Full classification. Very explicit, like a character table. Very explicit for those characters. You can get very more fancy pictures. So in case you remember the subgroups of S4, here they are. Or you don't remember, whatever. And here you get more fancy. So this is always a finite abelian group. It's always a Z mod P plus a Z mod Q or something like that. It's not so bad. It's a really, really explicit classification. Okay, what I solved for you, that's how you should think about it, is the group type case. So here no cell theory applies. It's just one block at the bottom. So I needed to solve that by hand in some sense. Like I would need to solve representation theory of a group by hand. Here's by hand solution. It's not so bad. It's not so bad. And this is what I would like to see showing up as ages, because then I can kind of get a classification along these lines plus cells, which is exactly as in the monoid. Okay, so that's what I want, right? And up for classification as before. There's one-to-one correspondence. I should have said that, okay, let me just write it down. I realized now that I should have said that. The apex theorem is still true in the setup. So every simple of one of my categories M has a unique apex. So that's still the same. It's not true, but the statement is still the same.
What's that category? What's the name?
What?
What's the name?
Apex. Okay, let me draw a picture. I have my cells, my little J cells. Okay. And if one element of my J cell, this is in my category S, in my category S, if one element of my J cell acts as 0, then all elements of my J cell act as 0. And the apex is a maximal J cell, everything below will not act as 0, does not annihilate the group. Everything above 0 and below 0.
Everything that's comparable to.
Yes.
Everything that's not below J annihilates. always your reference.
Everything that's not below J. That's right. It's not below J in Additive. So everything in the hopefully the second red.
So the above you have a tensor ideal.
Yeah, that's basically all.
And then below you have some like your maximum in this quotient by your tensor ideal.
That's right. Below you have not many functional elements. But upstairs it's zero. I have about 5 minutes left, you can see. And it's not exactly the same. Okay, I need to tell you what the replacement of an idempotent is. Some people were asking. Let me just write it down. Write down the picture for you. So here's the definition you see on the board. How you like to think about it is the following. So I have an object that I call D, and I have a map to my object from the identity, which I am very bold known as not. That comes somewhere from here from the identity. And having not messed up my notation, I now have some element F on the right that draws the string F. And D should satisfy a property with respect to F, and F is in the fixed left cell. Namely, that I can split it with the form of the picture. I can draw, if you want, a merge on top such that this picture equals the string.
Write the target.
And this implies that you would like to know that this T will be.
Okay, so on the slide you said you have a map from D to 1, but you meant a map from 1 to D.
I meant to map. No, I think my picture is it.
Okay. Is it okay either way? You have some duality?
Sorry?
Are they equivalent? You have some duality in your category, so.
And the lens is equivalent, yeah. So I messed up my picture. It should have gone the other way around. I'm saying I have a map to the identity as backpoints out, not from the identity. And that's a replacement for an idempotent. So there will be those little D's in my little boxes. And these are my idempotent. These are my shaded boxes in the other picture. I will shade all of these. These are all right. All of these SHs then will play a role.
I guess so. In particular, if F is equal to D, then D tensor D has D as a summand. It's not actually D, but it has D as a summand.
That's right. It's kind of categorifying idempotent. Right? So D tensor D is not equal to D, but it is D as a summand, which is a correct property. It knows itself. It might appear as many copies of pseudo idempotent. Exactly this definition of pseudo idempotent. These things tend to be unique. And in our example, the Dufresne evolution is a two-unit object. In general, they might be really crazy. They spread around in your category, but they play the role of idempotent. So what you need to do is you need to mark the cells where they appear. Exactly as in my pictures before. Make them whatever my color was, blue. We'll see it again in a second anyway. And just for completeness, in those things, it's a unit. This one, which is the next one, is p minus 1, p squared minus 1, p cubed minus 1. They're called the Steinberg monoids.
Why you call this monoid?
Sorry?
Why you call this monoid?
Because of circle bimodules. Give me a second, I will go to circle bimodules. So I can just answer it. So in circle bimodules, that distinguish evolution from Dufresne evolutions. And the Dufresne evolutions here are exactly those, and they correspond to the notions that we call in the 18th strongly. That's why they. A better name probably would be categorical pseudo idempotents or something, but that's what they're called.
D doesn't need to be indecomposable.
D doesn't need to be irregular or anything.
Indecomposable.
Sorry, everything I know right now is indecomposable. Otherwise, I put in more of them.
Because you can have like some of them, but you do that satisfied.
That's right. So everything I ever write down is indecomposable. I would like to leave it Okay, but I can also tell you why. I would like to draw those pictures, and those pictures are on the set of the proposal. Where?
Standard modules, they reduce for, right?
What is reducible?
Standard modules.
Yes.
This means that they have no non-zero maps to unit object.
These are not the standard. This isn't the finite example. These are different, I think. We can talk about it.
So,
Maybe I should call them Steinberg modules.
okay.
Yeah, let me just finish. So then you really get this classification statement. So, the symbols was an apex J and one-to-one correspondence was a symbol of those SHs. So the SH again, same picture, is almost my last slide. I have a huge matrix with matrix blocks and floors, matrix entries. I shade some of them. The ones with these matrices. They don't need to be anywhere nicely arranged. You completely random somewhere else. I have associated SH as my category. I have reduced the problem. That's what makes it actually go into zillions of more of those. And all of these are just classified by looking at the matrix. Exactly as in the monoid case, it's extremely great. I don't have any extra assumptions. Exactly as in the monoid case. Let me just show you one example, which I'm already something like 3 minutes over time, which I can't do in all the details. So, for example, you can apply it to circle bimodules. Here's my lightning summary of circle bimodules. There is a category where the indecomposable objects correspond to the Castanistic basis. We can discuss it later a little bit. But there exists the category, and the Castanistic basis is indexed by elements of the Weil group, of the Coxeter group. So this is fiat, and I would like to call this the Zögerle-Elias-Williamson theorem. So here's the expert on Zögerle bimodules. So it really follows from their work that 1, 2, 3, 4, it's fiat, and the set of indecomposables are the elements, correspond to the elements of the Coxeter group. Good. And you can write down exactly the same pictures that I had before, just the notion of an idempotent changes a little bit. Yeah. So I had this picture last time. This was a Castanistic basis, and we had a problem. It didn't really work. On the categorical level, the problem vanishes. It's amazing. It's really amazing. The problem vanishes. It's gone. Everything is fine, and the categories you see here. I'm lying a little bit now because I'm out of time. The categories you see here are exactly the ones we like to see. So vect, Z-mod 2, and vect, which is the following. It's really what we have seen before. It's a beautiful picture, the same as for the monoids. So I'm just saying vect is, of course, nothing else than rep of the trivial group. So we know classification for vect, rep of the trivial group. Super vector spaces, so vect Z-mod 2. Is the same as rep Z-mod 2, so we also know a classification here, by the previous result. And the group type object, again, plays exactly the same role, so I get exactly the classification I wanted. I can write down my little tables of subgroups, and cosine is all. And the same works for all Zögerle bimodules of finite time. You get more sophisticated categories, but and then zillions of other examples which I can't discuss.